Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. My name is Amir Khuzairi bin HASBULLAH, metric number 300 800, with my fellow presenters here, Muhammad FATHI AFIF bin Muhammad FAIZ, metric number 300 565, and ALYA FARHANA BINTI Muhammad AZMI, metric number 297 264. We are representing class ASQQM2033 for intermediate calculus, and we will be presenting about ordinary differential equations, also known as ODE. Let's get to it.
So let's begin with what exactly is a differential equation. It is an equation involving an unknown function, which may also be called a solution, and its derivatives. Some examples are shown below, such as a function of yx whose derivative is x, a function of yx whose derivative is y, and so on. So the solution for yx can look like something such as, let's say the first one, yx equals to 1.5 x to the power of 2 plus a constant.
So, why is it important to understand ODE? Well, it's because it applies in various fields, such as physics and engineering. Did you know that ODE describes how objects move when forces act on them? Second of all, ODE can be used to apply on economic growth and finance. You can use ODE model to know how economic variables like capital and investment change over time. Third one, you can use ODE for environmental science. ODE can describe how populations of animals grow or shrink over time. And fourth one is astronomy. ODE can explain how planets and satellites move in space. They describe how stars and galaxies evolve over time. And it's not just in these kinds of fields. It can also apply in biology and also can apply in chemistry and other types of fields. So that's why it's important for us to study ODE.
The order of a differential equation is determined by the highest derivative of the dependent variable with respect to the independent variable that appears in the equation. The order indicates the number of times the dependent variable is differentiated. Degree of differential equation is the highest power to which the highest order derivative is raised, provided the equation can be expressed as a polynomial in the derivative. The degree is defined only when the differential equation is polynomial in its derivative. So now look at equation 1. The equation is dy over dx plus y equals to 0. The highest derivative present in the equation is 1. So the order is 1, and then the highest power exponent of the derivative order is 1. So the degree is 1. Next, we go through for the equation 4. In this equation, the highest derivative power in the equation is 2. So the order is 2. And then the highest power exponent of the derivative order is 3. So the degree is 3.
So, there are four types of ODE. The first one is called separate ODE. The second one is a homogeneous ODE. The third one is exact ODE. And the fourth one is linear ODE. Now we will dive in deeper into each of these types of ODE. For the first type of ODE is called separated ODE. By the word separated, we're separating two types of function. So an ODE is separable if it can be written in the form of Fy dy equals to gx dx, which means on the one side of the equation is all y's, and on the other side of the equation are all x. So let's take a look on the example. The example given is an equation which is y plus 2 dx plus y x plus 4 dy equals to 0, given that y negative 3 equals to negative 1. So what do we do here? So by analyzing the question, we can slowly move everything up by shifting all the equations into separating them into one side is only y, one side is only x. As you can see, do we have the equation y divided by y plus 2 dy equals to negative 1 divided by x plus 4 dx. So that is what you call separated. Like I said, one side y, one side x. And then we can just integrate it, and then the next step that you can see until you get the function. And that is separated ODE.
Next on the list is homogeneous equation. In order for it to be a homogeneous equation, every term must be in the same degree. The example shown, the first one is 2x dy equals to x plus y dx. This is in the first degree. The second example is in a second degree, and the third example is actually also in the first degree. So moving on to the example and a solution for homogeneous equation. Given that derivative of y equals to 2x exponent negative y over x plus y over x for the point 1, 0, first what we do in order to solve this equation is we have to make sure to use y equals to vx and dy equals to x dv plus v dx and substitute this into the equation itself in order to solve this equation. Once you have reached the general solution of exponent y over x equals to ln x squared plus constant, we may now input the point 1, 0 in order to get the final answer, which is exponent to the power of y over x equals to ln x squared plus 1.
Exact ordinary differential equation ODE is the type of first order differential equation that can be expressed in the specific form, where the solution can be found directly by integrating. The key characteristic of the exact ODE is that it can be written in the form of a total differential, which means that there exists a function xy such that its partial derivative match the term of the differential equation. Now look at the example in the slide. For first one, we check for exactness and verify if differentiate m to y equals to differentiate n equals to x. Step number 2, find the potential partial function xy, and then differentiate the mxy and x plus y and xy. Since the my equals to nx, the DE is exact.
Now we've come to the fourth one, which is linear differential equation. The standard form is derivative of y plus pxy equals to qx. It combines an unknown function y and its derivatives with coefficients that are not necessarily constants but may be functions of the independent variable, in this case x. We require integrating factor ux equals to exponent to the power of px, integration of px dx, and the general solution y equals to 1 over ux, integration of integrating factor qx dx plus c in order to solve linear differential equation. So the example here given is the derivative of y plus xy equals to x is already in the standard form, and such we can already equate it directly, where px and qx are both equal to x, and the integrating factor can already be solved here such that it becomes exponent to the power of x squared over 2. Once we know what the integrating factor is, we can directly input it into the general solution.
Once we recognize the type of ODE, we can apply it on a daily basis on any type of problem. For this kind of example, we use a problem of population of bacteria that grows at a rate of proportional to its current size. If the initial population is 100 bacteria and the population doubles in 3 hours, what will be the population after 5 hours? So for the first step is we have to formulate the differential equation, which is dp over dt equals to kp. P is for population, T is for rate, K is for growth constant. Second, we solve the differential equation using the types of ODE we learned. For this one, it's separable. Now that we do it and then we integrate it, we'll get the answer for C using the initial population, which is 100. Second, we must get the value of constant by using the second sentence, which is population doubles in 3 hours, which is P3 equals to 200. After that, you'll get the answer for constant. So now once we have the constant and the C, now we can find the population after 5 hours. Just put in the value and then you'll get the answer.
The conclusion of ordinary differential equation are equation involving function and their derivative used to model various phenomena in the science and engineering. They are classified by order, highest derivative and degree, highest power of the highest derivative. Solving ODEs involve methods like separation of variable, integration factors, and numerical technique. Exact ODEs A specific type can be solved by finding a potential function. ODEs are essential of understanding dynamic system and are applied in the field ranging from physics to economic, providing insight into the behavior and evolution of complex system. Thank you.